Hello everyone. Welcome to this video on AT32 CAN FD Peripheral. The video comprises 3 parts. Part 1 covers the differences between CAN FD and CAN 2.0B, along with an overview of CAN features. Let's get started with the differences between CAN FD and CAN 2.0B. There is no remote frame for CAN FD. It supports data frame and extended identifiers. FD-FBit, FD frame format indicator, recessive value refers to CAN FD frame, while dominant value refers to CAN 2.0B frame or 0-bit in CAN 2.0B. BRS-bit, bit rate switch enable, it is used to switch to data or fast bit rate for data payload and the CRC of CAN FD frames. In CAN 2.0B, BRS is fixed. ESI bit, error state indicator, it indicates whether CAN FD node is error active or error passive. It is always 0 for CAN 2.0B. In data frame length, it is up to 8 bytes data payload for CAN 2.0 and up to 64 bytes for CAN FD. In CAN 2.0, its CRC is fixed at 15 bits. In CAN FD, its CRC depends on DLC length. In other words, the CRC is 17 bits for DLC equal or less than 16 bytes, and it's 21 bits for DLC equal or bigger than 20 bytes. For CAN FD, the stuff count is also calculated as a part of the CRC field. For CAN FD, its first protocol is called non-ISO CAN FD, proposed by Bosch. Its second protocol is called ISO CAN FD, used to overcome a few weaknesses of the first version. For CAN FD ISO frames, the stuff count is transmitted as a part of the CRC field. Because of the differences in CRC field, ISO and non-ISO frames are incompatible. Here are the main CAN features. First, basic functions. Up to 8 bytes payload for CAN 2.0B, up to 64 bytes for CAN FD, programmable frame rate, 3 clock domains dedicated to host interface, CAN protocol machine and timestamp, programmable baud rate prescaler, and interrupt sources. Second, transmission function. It has 2 buffers, PTB and STB. It is possible to stop frame transmission from PTB or STB in real time. Retransmission and re-arbitration times are settable. Third, reception function. It has a 6-level receiver buffer. Overflow mode is configurable. RBUF almost full warning is issued in case of overflow. All data frames, including error frames, can be received. It also comes with 16 separate programmable internal receive filters. Fourth, extended functions. It supports external or internal loopback mode, listen-only mode, status and error report, arbitration loss capture, programmable error warning limit, transceiver standby mode. It also supports CIA 603 timestamp, TTCAN. Here is a basic structure of CAN controller. On the right, CAN protocol machine is connected to a CAN bus transceiver to control its standby mode. On the left, host controller interface is connected to the CPU APB bus to output interrupt signals. The CAN controller has 3 clock domains. The first is host clock for the host controller. The second is CAN clock for generating bit time. The third is timer clock for generating timestamp. Meanwhile, there is also a receive path and a transmit path between CAN protocol machine and the host controller interface. The CAN controller offers an LLC as an interface between software and hardware. LLC refers to Logical Link Control Layer. LLC frames are exchanged between the host controller and the CAN controller. It is used for frames to be transmitted, for received frames, and to configure the acceptance filters. This table shows the definition of the Logical Link Control LLC frame with timestamp. It includes ID, format, FMT, type, TYP, payload data, CIA 603 timestamp, and cycle time for TTCAN. Note that the position of timestamps are dynamic at address offset position T. Receive timestamp and TTCAN period time are only relevant for RBUF. They have no meaning for TBUF and ACF. The address offset position T is dynamic depending on the payload length. This dynamic position T is always word-aligned and is obtained by reading format register. Example here, for 1 byte payload, The address position T is T equals 16 plus 4 equals 20. This table shows the LLC frame abbreviations. This figure shows a schematic of PTB and STB in FIFO mode. For how to access TBUF, take the following steps. Select PTB or STB using TBSEL bit. Write data frames to TBUF register. TBUF register can be written in any order. For STB, when SNext is set, it indicates that the current STB slot is filled. If STB not full, SNext is cleared by hardware. For PTB, write attempts can be repeated to overwrite previous data. Caution here, it is necessary to check whether TBUF is write locked before writing. For PTB, when TPE is set, meaning that PTB transmission is going on, PTB is prohibited to write. For STB, when SNext is set, meaning that STB is full, STB is prohibited to write. When transmit buffers are full, it is ready to send them. We use TPE bit to enable PTB transmission. For STB, we use TSONE bit to send a single STB frame, and use TSALL bit to transmit all STB frames. PTB always has higher priority than STB. With stat bit, you can get the status of STB. With SMOD bit, you can set STB priority. First, FIFO mode, frames are transmitted in the order in that they were written into the STB. Second, ID priority mode, the frame priority is decided by the ID of a frame. A lower ID means a higher priority of a frame. Here is an example code of PTB and STB transmission from our BSP. First, select the data frame to send by writing structure parameters, then write PTB or STB and send data. Finally, check the flag bit to confirm if it is successful. The CAN controller can withdraw the transmission request by setting TPA or TSA if the transmission has not yet been started. There is no abort while a frame is transmitted. Both TPA and TSA source a single interrupt flag, AIF abort interrupt flag. The CAN protocol machine execute an abort only if it does not transmit anything to the CAN bus. Setting both TPA and TSA simultaneously is not recommended. If an abort is executed, this results in two actions. TPA releases PTB, resulting in TPE equals 0. The frame data is still stored in the PTB after releasing the PTB. TSA releases one single slot or all frame slots if the STB. This depends on whether TSONE or TSALL was used to start the transmission. Stat will be updated accordingly. Releasing a frame in the STB results in discarding the frame data because the host cannot access it. To clear the entire STB, both TSALL and TSA need to be set. To clear one single STB, both TSONE and TSA need to be set. How to access RBUF? This is a basic structure of RBUF. Received frames are stored in the RB of A6 level depth. RB operates in FIFO-like mode. It is accessible through RBUF registers. Read RBUF register to get the earliest received frame. Set RREL to release the current RB slot and select the next frame next slot. Repeat these steps until the RST-AT bit indicates buffer empty. The RB buffer status is obtained by reading the RST-AT bit. When all 6 RB slots are full, the RFIF RBUF full interrupt flag is set. Receive buffer almost full status is configured using AFWL almost full warning limit, which has valid range from 1 to 6. When RBs are full and reach AFWL threshold, the RFIF almost full interrupt flag is set. When RST-AT indicates that RB buffer is full, an incoming new frame at this time will result in ROV RB overflow being set. When ROV is set, it means RB buffer overflows, and the new incoming frame is lost. The ROIF overflow interrupt flag is then set. To handle data lost in case of overflow, the ROM bit needs to be configured. First, the oldest frame will be overwritten. Second, the new frame will be discarded. This is an example code of access to RBUF. First, enable RIE and then check the RIF flag to read or release RBUF. Note that all data in the RB must be emptied by repeated access attempts. Then let's take a look at how to access ACF acceptance filter. The ACF consists of an acceptance code field, ACFC, and acceptance mask field, ACFM. Both code and mask together define one acceptance filter slot. Both ACFC and ACFM contain a header of ALLC frame. ACFC refers to the unmasked part of the received LLC frame. It must match this code to be accepted. Otherwise, it will be filtered. ACFM, if the mask bit is 1 minute, the corresponding code bit is ignored, don't care. If the mask bit is 0 minutes, it is compared with the incoming LLC frame filter enabled. In this figure, data must pass through ACF before reaching RB buffer. There are 16 ACF pairs, ACFC plus ACFM, each with a corresponding enable switch AE0 to AE15. Note, ACFC and ACFM can be written only when reset equals 1. This is an example code demonstrating how to configure ACFC and ACFM. First, enable software reset, configure filters by writing to code and mask parameters, then write ACFC and ACFM. Finally, enable filters after clearing software reset. The CAN controller has 4 interrupt vectors. Each interrupt source can be enabled or disabled individually via the interrupt enable register in 10. The interrupt flag is cleared by writing 1. The 4 interrupt vectors. First, transmit interrupt vector. It includes 4 interrupt events: primary transmit interrupt flag, TPIF, secondary transmit interrupt flag, TSIF, abort interrupt flag, AIF, and arbitration lost interrupt flag, ALIF. Each can be enabled or disabled individually. Second, receive interrupt vector. It includes RB almost full interrupt flag, RAFIF, RB full interrupt flag, RFIF, RB overflow interrupt flag, ROIF, and RB receive interrupt flag, RIF. Each can be individually enabled or disabled. Third, error interrupt vector. It includes error interrupt flag, EIF, bus error interrupt flag, BEIF, and error passive interrupt flag, EPIF. Each event can be enabled or disabled individually. The EIF flag will be set under the following 2 conditions: when the error counter crosses the error warning limit, either above or below; when the bus-off bit is set or cleared by hardware. Fourth, status interrupt vector. It has 3 interrupt events: time-triggered interrupt flag, TTIF, window-triggered interrupt flag, WTIF, and trigger error interrupt flag, TEIF. Each event can be enabled or disabled. These status interrupts and flags are only used in time-triggered CAN mode. Thanks for your watching. With this, we come to the end of part 1. Please stay tuned for part 2 coming up next.